Welcome back. At first, happy Poila Boishak. May your life be blessed with happiness and fulfillment, and wish your dreams and your aspiration come true on this festival. So, happy Poila Boishak again. Today's goal of this lecture. In my previous video, I have seen some shortcut trick of inner product to define which of the following space be inner product. Such type of example I had seen in my previous video. The shortcut rule. More example I had solved by the positive definite property, by this property. In my previous video, I have seen at first check positive definite. If this is break, then you can tell this matrix be not inner product. And if the positive definiteness be satisfied, then we can approach another method. Okay? At first, I will tell you, please pay attention in this topic. If you pay attention, then you can understand in better way. Because this type of example actually very important for not only comparative exam, this type of example are very important for also higher study. Okay, now I will see matrix representation of an inner product, and today's goal of this lecture actually this. By matrix representation we can easily construct inner product space. Let A be M cross N matrix and A transpose be the N cross M matrix. Then standard inner product in Rn, we all of us know, inner product UV equal to U transpose B. And we all of us know also, we can write, if we consider A be M cross N matrix and X be the Rn and Y be Rm, then inner product Y with Ax is equal to A transpose Yx, and this is the inner product in Rm and this is the inner product in Rm. Inner product U with V is equal to U transpose V, and we can write this as by this inner product, because here U be the member of Rn, therefore we can write it as the combination of bases U equal to summation Ui Ei and V equal to similarly Vj Uj. Therefore inner product U with V equal to summation Ij 1 to N. Here this would be Ui Ei Vi Vj Ej. That means this combination of Ei Ej, consider this is Aij Ui Ej Uj, and this is actually AU dotted with V, and AU dotted with V means AU transpose V, where AU transpose is 1 cross N matrix and V is N cross 1 matrix, and AU transpose means U transpose A transpose V, and since A is symmetric matrix, so we can write A transpose equal to A, therefore U transpose AB. Therefore let A be symmetric matrix, then UV, coordinate UV transform to inner product UV, which is actually U transpose AV, and U transpose AV means AU dotted with V. Therefore inner product UV, we can write this as AU dotted with V. And today's goal of this lecture, today I will say let x equal to x1, x2 up to xn and y equal to y1 or y2 up to n, which denoted the vector space in Rn. Then for a fixed vector n greater than equal to 2, which of the following define an inner product space on Rn? Option 1. Notice, this question I had seen in my previous video, and I had solved this question by positive definiteness. But today I will say this question by matrix representation, and then I will check is the matrix is positive definite. Actually, I will solve the question by positive definiteness. This is same way, but this is some trick. Here I will consider matrix representation. I hope my all viewers have understood. In my previous video I had seen this question, inner product x, first option, inner product x y equal to summation ij 1 to n xi yj, which is equal to x1 y1 plus x1 y2 plus x2 y1 plus x2 y2. We can write this equation by matrix representation such way. For short calculation, I have considered it n equal to 2, because here in my previous video I had also considered n equal to 2. If you don't see my previous video, at first see my previous video, then today's video would be so easy. Notice, here I have considered it n equal to 2, so the equation x1 y1 plus x1 y2 plus x2 y1 plus x2 y2, and the matrix representation would be such type. Here x1 y1 here y1 y2, that means the equation 1 1 1 1. Therefore, we have to verify the positive definiteness, and we all of us know A be 2 cross 2 symmetric matrix, then the matrix A is positive definite if A and D greater than 0 and determined AD minus B square greater than 0. Then we can tell the matrix, obviously this matrix would be symmetric matrix, so the matrix would be written such type AD BB. If it follows such way, then we can tell obviously this matrix be positive definite. So here we have to check the positive definiteness. For positive definiteness, notice this matrix obviously be positive, obviously be symmetric. Here all entries be positive. So first condition of positive definiteness, AD greater than 0, 1 1 greater than 0, this is true. And notice determinant equal to 1 minus 1, this value equal to 0. Since determinant of equal to 0, so this break the positive definiteness. So by matrix representation we can tell easily this is not be inner product. I hope my all viewers have understood. This is very easy way. So today also I have defined this method by matrix representation, because if you construct the matrix representation, then it is very easy to define a matrix, a inner product, which of the following be inner product or not. And second example, x with y equal to summation ij 1 to n xi whole square plus yj whole square. This is actually equal to x1 square plus y1 square, x2 square plus y2 square, x1 square plus y2 square plus x2 square plus y1 square. And this is actually written as 2 times x1 square plus y1 square plus x2 square plus y2 square. And inner product xy equal to, since here 2 times x1 square plus y1 square plus x2 square plus y2 square. Therefore, here we cannot construct the matrix. Since we cannot construct here matrix, so previously in such way I have defined this is not be inner product. I had told you when square term, then always it would be break the linear property. In my previous video I had solved this. This is always break the linear property. That means alpha x y, this is not equal to alpha times inner product xy. So we can tell this is also not be inner product. Third example, inner product xy equal to summation j equal to 1 to n j cube xj yz. This means we can write it as x1 y1 plus 8x2 y2, which with us also matrix representation x1 x2 here y1 y2, and the matrix representation would be such type 1 8 0 0. Notice here A means 1 and D means here 8. 1 8 greater than 0. Also determinant of the matrix is 8, which is also greater than 0. Therefore all property of positive definiteness has satisfied here. So we can tell easily by matrix representation this is be the inner product. Next, inner product xy equal to summation j equal to 1 to n xj y n minus j plus 1, which we can write as x1 y2 plus x2 y1. The matrix representation would be such way. Here the inner product is x1 y2 plus x2 y1. Therefore the matrix representation would be x1 x2 y1 y2. Here the matrix representation would be such type 0 0, here 1, here 1. Notice here the first condition of positive definiteness has broken. So this is not be inner product. I hope my all viewers have understood why matrix representation to define which of the following be inner product. This is very easy method. I hope my all viewers have understood this is clearly. If you can to verify the matrix, then obviously this is very easy method. Which of the following be inner product or not? Okay. Our next example, let inner product Rn cross Rn to Rn denote the standard inner product space on Rn. And for a non-zero vector W belongs to Rn, define TW from Rn to Rn by TW equal to V minus inner product 2 times VW divided by inner product W with W times D for non-zero vector V in Rn. Then which of the following are true? Option 1, determinant of TW equal to 1. Option 2, inner product TW with the vector V1 comma inner product TW with the vector V2 equal to inner product V1 V2 for all V1 V2 belongs to Rn. Option 3, TW equal to TW inverse. Option 4, T to W equal to T to TW. For this question, for short calculation, here also I will use n equal to 2, because if this is true for n equal to 2, then this is true for all n. Consider T, who is defined from R2 to R2. Here the linear transformation denoted as TWV, which is equal to V minus 2 times inner product VW divided by inner product W with W times W. And this is true for all V belongs to R2. Then since here TW defined from R2 to R2, Here the basis vector in R2 we all of us know 1 0 0 1. Similar to before, since here the transformation is this type of transformation, by this basis vector construct one matrix representation. That means if we can construct matrix representation of this linear transformation, then we can easily verify this type of option. Notice TWV. Here the basis vector, since T defined from R2 to R2, here the basis vector of R2 is 1 0 0 1. For this linear transformation, at first, since here TWV fixed the vector 1 0, then TV1 would be, at first with respect to this basis vector 1 0, TV1 means T10 actually, V1 means 1 0, since inner product V with W, that means since the vector here R2 to R2, here V1 is 1 0 1 0 with 1 0, because I have considered the W vector is 1 0, that means this value would be 1. Inner product V with W is 1 divided by inner product W with W 1 0, this value also would be 1 times 1 0. Therefore this value is T of 1 0 is, here minus 2 times inner product V with W, so here also would be 2. So this value would be, minus 1 comma 0, and T of 0 1 equal to V, here the vector 0 1 minus 2 times inner product V with W, here 0 1 with the vector 1 0. This value would be 0, and this value 1, and this value is 0 comma 1. Therefore this value is, here the value would be zero comma 1. So with respect to the basis vector, the matrix representation is minus 1 0 0 comma 1. This is the matrix representation with respect to this basis vector. And notice determinant of this matrix is minus 1. So here the linear transformation is TWV since. So determinant of TWV is minus 1. Now notice the option. This matrix is actually orthogonal matrix, because notice the matrix here, length of the vector each column is 1, and dot product of the vector is 0. So obviously this is the rules of orthogonal matrix. Length of vector is 1 and dot product of the vector is 0. Since this matrix is orthogonal matrix, therefore TW times TW transpose equal to identity. Therefore this implies TW equal to TW inverse. Option 1 is a wrong option. Option 3 is a right option. And we all of us know, since the matrix is orthogonal matrix, so option 2 also right, because it preserves always the length. Next, TW equal to 2 times TW. At first, just check what is the T2W. T2W V equal to V minus inner product V with 2W divided by 2W times 2W with the vector 2W. Then this is equal to, here just cancel 2 times 2, that means this would be 4. Here 4, here 2. Here also 2, just omit, this would be cancelled. Then this would be V minus inner product V with 2W divided by inner product W with W times W. And by the property of inner product, we can write this as V minus 2 times inner product V with W divided by W with W minus times W. And this is actually nothing but this is actually TWV. Therefore, I have got T2WV equal to actually TWV. Therefore, option 4 is a wrong option. T2W not equal to 2TWE. This is actually equal. That means only option 2 and option 3 is a right option. I hope my all viewers have understood this is clearly. Okay? Oh yes. I will stop here. I hope my all viewers have understood matrix representation of an inner product space. See you soon. Stay safe and stay positive always, and don't forget to subscribe my channel for more videos. Thank you so much and Shubho Navabarsho again.